Welcome back to our class. Let's continue our discussion for the key technical challenges to optical communication in the next decade. In this chapter, we will continue to discuss the fifth trend, how to digitally and intelligently evolve optical networks to build an efficient system capable of accurately sensing network status. First of all, let's take a look at some common problems facing the communication industry. The main problem is the OPEX, that is, the operation and maintenance expenditure. The total expenditure and cost of device maintenance are increasing, which is mainly reflected in the following three aspects: low resource utilization, high energy consumption, and low O&M efficiency. First, resource utilization, that is, bandwidth elasticity. In the early days, we reserved fixed bandwidth for services. The actual traffic on the network is far lower than the bandwidth we provide. As a result, the utilization rate is low, causing waste. The second is energy consumption. The entire set of network devices that we deploy are always running regardless of network traffic. With the large-scale deployment of 5G and data centers, operators are spending more and more on energy consumption, and reducing energy consumption has become the focus of operators. The last one is operational inefficiencies. The telecommunication network has more and more layers and connected more and more complex. However, the network O&M still depends on manual troubleshooting. Manual fault locating, troubleshooting, and service restoration also require manual processing. There are no preventive O&M measures. When the network scale increases exponentially, if the traditional manual O&M mode is still used, the O&M team will face great challenges. These three problems are common to telecom networks. For optical networks, there are three major challenges. First, the customer experience is poor. Traditional optical networks provide only dumb pipes that carry carriers' own services, such as SDH, IP-RAN, and data networks. They do not directly reach carriers' customers. However, with the increasing demand for high bandwidth private lines, optical networks move from the background to the foreground and directly provide services for carriers' customers. We find that these private line service customers have different requirements for services. They require more agile provisioning, quicker troubleshooting, and service recovery. This brings great challenges to the improvement of user experience for the optical networks. Take the service provisioning as an example. A customer applies for a private line from a carrier, and the carrier handles the service request. Then the carrier performs planning based on the application, and then deploys and uses the private line service. The service provisioning process may take as long as 2 months. How long will the client give you? Maybe they only give you 2 or 3 days. The second one is the issue of resource efficiency. In terms of network architecture, traditional optical networks are mainly chain-shaped ring networks. With the deployment of private line services, our optical networks gradually evolve to mesh. Traffic congestion occurs in core areas, high channel utilization, and difficult capacity expansion. The space and power supply of up to 60% sites are limited. In addition, the reliability is low. For example, a carrier experiences up to 300 fiber cuts every week. The last one is low O&M efficiency, which is the most discussed challenge. Most optical network O&M is still performed manually, which is time-consuming and labor-consuming. The number of NEs increases by 15% every year, and the O&M expenditure is also increasing. In addition, most network faults are caused by misoperations 90% of network O&M is post-event O&M. In other words, the efficiency of solving problem is very, very low. To quote a former Huawei employee, he is now the chief architect of a Canadian carrier. We are the 21st century network and the 18th century network O&M. To address these problems and challenges, we believe that digital reconstruction of optical networks and the incorporation of some artificial intelligence technologies will be a trend in the future. We have mentioned AI here. Is optical networks suitable for AI applications? The answer is yes. The application of AI has three requirements: algorithm, big data, and computing power. The current algorithms, computing power, and big data storage are ready. Rich AI algorithms are available in the industry to cover end-to-end scenarios such as deterioration analysis, fault prediction, intelligent commissioning and rerouting, and also fault root cause analysis. In terms of big data, the optical network can report thousands of parameter collection information per second to display the status changes of the optical network in real time. In terms of computing power, there are many AI chips in the industry. We only need to deploy them in optical networks. In addition to these 3 points, the inherent characteristics of optical network are also natural and favorable conditions for intelligent transformation of the optical networks. First, there is a large amount of data in the optical network. They changes dynamically and in real time, like the receive and transmit power, the power consumption of the equipment. Signals in an optical network, such as optical power and optical cable loss, are analog signals. They are unstructured data. In addition, in an optical network, there are hundreds of states and parameters that can be adjusted and optimized by using an artificial intelligence model. Above, we explain the feasibility of introducing AI into optical networks. Next, let's introduce several levels of optical network intelligence based on the development of optical network intelligence in the industry. It is actually divided into 3 layers. First, we need to build an optical network digital base that can sense a large number of parameters to collect a large number of optical network operating parameters. In other words, the physical network of transmission equipment needs to construct the capability how to collect this data, provide the collection interface, and collect these parameters. These parameters including optical power, optical signal-noise ratio, polarization mode dispersion, nonlinear effect, reflection insertion loss, and bit error. Compared with the original performance data collection, we need to collect more data at a higher frequency so that we can accurately reproduce optical network analog signals. The second part, for each scenario, a model should be pre-built by using different algorithms, and the collected massive optical network parameters are input into these models. The model will be trained, and the parameter of the model will need to be adjusted according to the training result. Through continuous iterative training, finally, the model can meet our accuracy requirements. Based on the model constructed in the second part, various applications can be combined, such as real-time visualization of the various parameters, optical fiber attenuation prediction, deterioration diagnosis, and prediction and automatic optimization after fiber deterioration. These are the 3 modules for intelligent optical networks. Currently, several major manufacturers in the optical communication industry, we are actively investing resources in intelligent optical networks. Right now, we have made a lot of progress. However, there are still many challenges and problems to be resolved in the current intelligent optical network. An important point is that the precision of our model is not high enough. For example, the accuracy of fault prediction is only 90%. For telecom network, especially our optical networks, the service we are carrying, all these services are high value services. They have high requirements on the reliability and the service availability. So currently, the accuracy is still far from being applied on the live network. We also need to continuously optimize the algorithm models and adjust the parameter to improve the accuracy. Next, let's look at an intelligent alarm O&M solution. With this solution, you can better understand how to apply artificial intelligence in the optical networks. In this example, we hope that with the help of AI, one work order for one fault or one event for one fault on the optical network can be implemented. Through AI analysis, O&M personnel can be directly informed of the possible causes and handling method for this fault. This can reduce the skill requirement for the O&M personnel. So how exactly does this system work? Generally, the fault handling of the optical network is based on alarm analysis. Identify the fault cause and then locate the fault cause one by one. On a large scale network, there may be hundreds of or thousands of NE. If a fiber cut occurs, hundreds of alarms may be reported at the same time. In this example, a maximum of 100,000 alarms are reported on the customer network every day. So the first step is to classify and filter these alarms by the severity. Filter maintenance alarms and suppress idle alarms. So after major alarms are filtered out, we know that when a fault occurs, multiple alarms are generated along the signal flow. These alarms are correlated with each other. Based on this logic, we further aggregate the alarm by using multiple algorithms and classify the faults into multiple categories based on the aggregation rules and aggregation results. For example, service interruption fault, hardware faults, and NE unreachability faults greatly reduce the number of alarms and faults that need to be handled. Based on these fault scenarios and experience input from O&M expert, the possible causes and handling solution of each type of fault are provided in a hierarchical and time-based manner. This can simplify one work order for one fault. Finally, let's make a brief summary. In this chapter, we first discussed the low resource utilization, high energy consumption, and low O&M efficiency for the telecom industry. For optical networks, private line service provisioning is very slow, and user experience is poor. The network capacity expansion is difficult due to the network congestion, and manual network O&M is inefficient. To solve these problems, artificial intelligence technology is introduced into optical networks, and the construction of intelligent optical network is a development chain. Optical network has several inherent features, such as massive optical layer parameters, dynamic simulation systems. These are suitable for introducing AI technologies. We also introduced the concept and research direction for the optical network digital intelligence. They can be divided into three layers. First, we need to build a digital foundation for sensing and collecting optical network data. On this basis, we conduct mathematical modeling, train the models with the data, and combine these trained models. This feature applies to actual network O&M optimization and other scenarios. Finally, we use a case of intelligent alarm O&M. From this case, we learn the typical application scenario of artificial intelligence in optical network. That's what we have covered in this section. Next, let's use two questions to consolidate the contents for this section. First, it's a single choice question. Which of the following is not included in the three basic elements of AI? A. Big data. B. Algorithm. C. Storage. D. Computing capability. This is a simple question. AI has three elements: algorithms, big data, and computing power. Storage is not exactly the same as big data. It's only part of the big data. So the answer is C. The second question is a multi-choice question. Which three inherent characteristics of optical network are suitable for introducing AI? A. Dynamic system. B. Analog signal. C. Digital signal. D. Massive parameters. E. Ultra-high bandwidth. So optical network has several main features, including dynamic systems, analog signals, and massive parameter. The remaining digital signals and ultra-large bandwidth, they are not the main features. So the answer is A, B, and D. Well, that's all for this chapter. Thank you.